Swayam Prabha. Digital India. Educated India.
And if this is true for integers, then just by looking at the columns where these integers fall, by the definition of addition, it is a case that the column AU false plus the column MV false is the column 1 false according to the addition of columns. But the column MV false is the 0 column, and that's the identity element. So what you're left with is a column AU false is the same as the column 1 false, and the column AU false is the column A false times the column U false under the definition of this product. That is a definition of this multiplication, modular multiplication. So if there exists UV such that this holds, then there exists UV such that this holds. There is no V here. So so this statement implies this. Conversely, if you take this statement, what is it saying? It's saying, okay, so this I can rewrite as a column where AU falls. So the column where AU falls and the column where 1 falls are the same, which means they are congruent to each other modulo M, which means the difference between AU and 1, so AU minus 1, is a multiple of M, which means there is some V such that or some say minus V such that AU minus 1 is M times that minus V. Right? So if this is true, then this is true. So these are all equivalent statements, and that's all this is saying. So this is actually saying that multiplicative inverse of AXs, right? And this is saying A and M are co-prime with each other, and they are equivalent conditions. As an example, say 2 and 5, their product is 10, which modulo 9 is 1. So 2 inverse is 5 and 5 inverse is 2, and this condition would say, okay, for that 2 should be co-prime with 9 and 5 should be co-prime with 9, and indeed that is the case, right? So this is just one example of that happening. Another interesting consequence of this equivalence is to consider the case when M is prime. So if M is prime, then for every A other than 0, GCD of A and M, so every A in the range 0 to M minus 1 other than A equal to 0, so all the integers 1, 2, 3 up to M minus 1, they all are co-prime with M, because M doesn't have any other factors other than 1 and M. So all these other things, their only common divisor with M is 1. So the GCD is 1. Okay, so that means every integer A or every column labeled 1 to M minus 1, so everyone other than 0, they all have multiplicative inverses, right? So for a prime modulus M, all except 0 have inverses. 0 cannot have inverse because 0 times anything is 0, so you cannot have 0 times something equal to 1. So 0 doesn't have multiplicative inverse, but every other value has a multiplicative. Now we'll use the Skippy Clock example from the introductory lecture to explore and understand modular arithmetic a little bit more. So let me start with reminding you what congruence classes are. So for some modulus M, which we think of as a positive number greater than 1, you can define, for any integer A, you can define its congruence class denoted by this box subscripted with M, which is just a set of all integers which are congruent to it modulo M. Okay, so let me start by putting out all these congruence classes on the face of a clock. So my example is going to be modulus 7, and I start with 0, and these are the 7 integers, all falling in different congruence classes. But I can keep going. I look at all the other next set of 7 integers, and as you can see here, I put 7 above 0 because they belong to the same congruence class, and 1 and 8 are together, and so forth. And I can keep going. So I can keep going infinitely, and I get 0, 7, 14, 21. All of those would be congruent to 0. And I can also go backwards. So from 0, I can go to -1, -2, and so forth, and spiral in. And what you see here are what used to be the columns in a table from the last lecture. So instead of arranged as columns in a table, now all these numbers that belong to the same congruence class are stacked up along the same angle on this clock. Okay, so and I can the way you would go around the clock is you go 0, 1, 2, 3, 4, 5, 6, and then you spiral out and continue 7, 8, 9, and so forth. And here you could also spiral in and come in. Okay, and this is a nice way to visualize modular arithmetic. And by the way, so the labels for each of these congruence classes, the standard label for it would be the integer that's in the range 0 to m-1. So that's the that's what the remainder gives you. Okay. Okay, so to see a modular operation, so let's consider modular addition. So remember, to add 2 of these congruence classes, I take some representatives in them and add them together and see which congruence class it falls in. Okay. So let's take these 2 examples here. So this is a congruence class for 4. There's a congruence class containing 1, and I want to do 4 plus 1. And I would get 5 according to this definition. So I would get the congruence class containing 5. Right? That's the sum of these 2 congruence classes. And I could have done it, so that looks like I started from this congruence class and moved it 1 to in the clockwise direction, right? And I ended up in the blue one. I could have done this differently. I could have, instead of taking 1 as the as B here, I could have taken any one of them. So I could have taken -6, for instance. Okay, then I want to move this congruence class -6 steps, or that means 6 steps in the anti-clockwise direction. So I would go around, and so from 0 I come down to -1, -2. So that is 4 minus 6 is -2, right? So that's what I did by going counterclockwise. And I would end up with -2, but it lies in the same congruence class. Okay, so this is just a way to visualize modular addition. So the point is, you don't care about along how far away from the center you lie. You only care about the angle where you end up with. That's what modular operations give you. Okay, so now let's go back to this question we had, the Skippy clock. So there is a clock with m digits, numbers on its dial, 0, 1, 2, 3, up to m-1. And it has a needle that starts off at 0 and moves n hours at a time. Okay, and our question was, will the needle reach all the hours? And one specific example we had was this, where m was 13 and n was 2. And let's answer that question. So first I claim that all I need to check is if the needle reaches 1. So the needle will reach all the hours if and only if it reaches 1. Why is that the case? Well, firstly, if it reaches all the hours, then it must reach 1. Conversely, if it can reach 1, so from 0, it went around and at some point it reached 1, then I can repeat those steps to go from 1 to 2, and then repeat that set of moves to go from 2 to 3, and so forth, right? So if I can reach 1, then I know that I will be able to reach every one of those every one of those numbers eventually. Okay, so this question now, will it reach all the hours, is exactly the question of will the needle reach 1. And what does it mean to reach 1? It means there is some number of steps, t steps you can take, such that, so at each step you move n numbers to clockwise. So you would end up with something, you would have moved over, you would have reached nt, except you are working modulo m. So, you look at the remainder of nt modulo m. That's the position you would reach, and question is, would that position be 1 for any t? So does there exist a t such that nt is congruent to 1 modulo m? Okay, and here's the answer for that. The answer is that that'll happen if and only if m and n are co-prime. So the GCD of m and n equals 1. So why is this? So we already saw this, that GCD of m and n equal to 1 is the same as saying n inverse x's in Zm. So in this universe of congruence classes, multiplicative inverse for n x's if and only if m and n are co-prime. Okay, and this was an easy consequence of Bezos' identity. So we went over this last time. Now, one thing to notice is that the inverse of n, which I'm writing as v here, it's a remainder of v with respect to m. Now, v itself could be a negative number for all that we know, right? Or it could be much larger than m also, but the congruence class could be represented by the remainder, which is a number in the range 0 to m. So this n inverse can be taken as a number in the range 0 to strictly less than m, so 0 to m minus 1. And then n times t makes sense. So t is a non-negative integer. So n times t is some number of steps, t steps you would have taken, right? Skipping n hours at a time. So the fact that n inverse exists tells you that indeed there is a time which is actually in the strictly less than m time steps, and some positive number of time steps in which you would reach 1. Okay. All right, so that's the answer. We are kind of done with that question. However, it kind of it doesn't fully answer everything about the Skippy clock. So in particular, what if suppose m and n are co-prime, so then we know that it will eventually reach every number. But how long will it take to reach all the numbers, all the hours? So the way we reasoned about it is we said, okay, if you reach 1 eventually, so in t steps, t is n inverse, in t steps you would reach 1, and then in another t steps you would get to 2, and then another t steps you will get to 3, and so forth. Well, that's not the that's not necessarily the first time you would be reaching 2 or 3, right? You would have already passed through them earlier. So what's the least number of steps you need to reach all the hours? Okay. And this is also only talking about when you can reach all the hours. What if the m and n are not co-prime? Then it cannot reach everywhere, but in particular it cannot reach 1. But which all numbers can it reach? And how many numbers can it reach in particular, right? And here's another question. We know that eventually, if you run this clock long enough, infinitely long, there are only finitely many hours on the dial. So you will have to repeat numbers, right? Um, and what is a first number that gets repeated? Okay, what's the first hour on the dial that gets repeated for this needle? Okay, all right. So let's see how to answer all these questions. And the key to understanding this is looking at the multiplication table of Zm. So let's take this example of what we have, m equal to 13. Okay, here is a multiplication table for m equal to 13, and we are interested in n equal to 2. Okay, so I look at so what's the needle going to do? It starts from 0, then it goes to 2, then it goes to 2 times 2, and then 3 times 2, and 4 times 2, and so forth, right? So if you think of this, the column index as the time step, what is in this row is telling you the position of the needle at that time step. So at time step 0, it is at position 0. At time step 1, it is at position 2, then 4, 6, 8, 10, 12. And at time step 7, it is at position 1, and then 3, 5. So, at time step t, it is at position nt modulo 30, right? So it is at 14, the remainder of 14 with respect to 13 is 1. Okay, that's why it's at position 1. Okay, so this multiplication table is exactly telling you the positions of the needle at various time steps, where the row of interest for us corresponds to the n, the number of steps, number of hours that the needle moves in a single step. So, so when how long does it take for it to cover everything? So if you look at this, row here, you would actually, if you look carefully, you would see that by the time I've taken 12 steps, I've actually covered everything. All 1, 2, 3 up to 12 show up here. And I started from 0, so I would have covered every hour after taking 12 more steps from the start. Okay. And is that a coincidence that for 2 it happens so? Actually, you can take anything else. You say you take 3 here. Again, you would see that okay, 3 is co-prime with 13. In fact, everything listed here other than 0 is co-prime with 13, because 13 is a prime number. So 3 is co-prime with 13. At some point, it will reach 1. After 9 steps, it will reach 1. But not just that, after 12 steps, it would have reached everywhere. Okay. So why is that? We have already talked about GCD of m and n being 1, being the same as saying n inverse, the multiplicative inverse for n exists in Zm. And I'm claiming that that is actually the same as the following statement, which says that for any hour z, so think of z as a number on the dial, for any number z, there is some time step t such that you would reach it. And not just that, this is all happening in Zm, so this t is an element in Zm. So it is somewhere in the range 0 to m minus 1, okay? So, and this equality is in Zm, so, it's, in terms of integers, it's congruence modulo m, okay? So this statement here is saying that, within m steps, so t equal to 0 to m minus 1, I would have reached every hour z, right, by moving n hours at a step. So why is this? Let me just show that these two are actually saying the same. So one direction is pretty easy. If this is the case, if for every z this is true, then in particular for z equal to 1 it is true. And what does it mean to be true for z equal to 1? So nt equals 1. There is a t such that nt equal to 1. That's the definition of n inverse, multiplicative inverse, right? So you can take z equal to 1, and the corresponding t is the multiplicative inverse of n. In the other direction, it's because I can solve this equation for t as follows. I set t equal to n inverse times z, right? So if I substitute n inverse times z, which is a valid element in Zn, so what do I get by associative multiplication? I have n times n inverse times z, and n times n inverse is 1. So it's 1 times z, which is z. Okay, so this is a solution. So it is indeed the case that for every z, you can solve for t, provided the multiplicative inverse for n exists. Okay, so these are all equivalent statements. So what you need to just remember is that when m and n are co-prime in the multiplication table for multiplication modulo m, the row for n looks like this. Every integer shows up, every integer in 0 to m minus 1 shows up in this row within the first m columns there, right? And so it's true for 0 also. This statement is for every z. And since everything appears once, and there are only all m of them need to appear, and there are only m columns, there are no repetitions. There's what you're seeing here is a permutation of 0 to 12 sitting in that row, and every row will look like that. Every row will be a permutation of 0 to m. Every row such that n is co-prime with m. Which in this case happens to be every row other than n equal to 0 because m is prime. All right, so that answers our question. How long will it take to reach all the hours? You will take m minus 1 steps in addition to the starting position. So the first m positions you would reach will cover all the m hours. They will all be distinct. And okay, so what if m and n are not co-prime to each other? So how, in this case, we know that you will not reach 1 and you'll not reach everything, therefore. But which ones will you reach? Which positions would you reach? So let's take another example where, m, the modulus is not prime. So I've taken m equal to 8. And indeed, now there are values of n which are not co-prime with n, in particular, every even n. So let's say n equal to 2. You would see that it reaches 0, 2, 4, 6, and then the same positions repeat. So you don't reach anything other than these 4 positions. And if you took 4, you would see it reaches only 2 positions, 0 and 4. If you took 6, it reaches, again, 4 positions, 0, 6, 4, 2, same as what 2 did, right? On the other hand, all the odd ones, they are co-prime with 8. They reach everywhere. But we are interested in the ones which are not co-prime now. Where all do they reach? So so these were the 2 examples I mentioned. So let's say m and n have a common factor greater than 1, and let's say the GCD is g. Okay, some number in fact, g could even be 1 for what I'm going to analyze, but for the case GCD, for the case g equal to 1, we already saw what it looks like. So the interesting question is when g is greater than 1. Okay, so some integer greater than 1. Well, in this case, what do we know? So GCD of m and n are g. So g is a common factor. So I can write m as g times p and n as g times q. And further, p and q shouldn't have any more common factors, because if they did, then g will not be the GCD, will not be the greatest common divisor, right? I could take the GCD of p or some common factor of p and q and multiply that to g, and that'll still be a divisor of common divisor of m and n, and g will not be the greatest one there. So we know, since g is a GCD, p and q cannot have any more common factors. Okay, so let's let's write that down. And now I'm going to look at a new clock with this p and q instead of m and n. So it has p hours on the dial, and the needle moves q hours at a time. Okay, so it's a smaller clock, presumably. And I built this clock after you told me what m and n are and what their GCD is. I built a clock with P and Q there, such that P and Q are co-prime with each other. Now in this clock, the needle does hit every hour, right? However, what is its connection to the original clock? Well, if I took this new clock, the smaller clock, and subdivided every hour into g hours, that's like magnifying this clock by a factor of g. So in the new clock, what used to be hour 1 now looks like hour g in the magnified clock, and 2 becomes 2g and 3 becomes 3g and so forth. And further, in the new clock, the needle moves by q steps. In the magnified clock, it will move by qg steps, that is n steps. And the total number of hours in the new clock, there are p hours. When I magnify it, it'll have g times p, so it has m hours, right? So the magnified clock is actually the original clock. By magnifying, I mean every hour has now been subdivided into g hours. So you just think of it as going and painting in more hours between each hour of the new clock, and that would be that. What you get would look exactly like the old clock. Okay, if you forget the numbers, if you just look at the labels, the divisions of the hours, it has m hours on the dial, and the needle is moving n hours at a time. Okay, so now I can reason about this, what happens in the new clock, what happens in the original clock, by thinking of what happens in the new clock, because the original clock is exactly the same as the new clock. It's just that it has a few more hours painted in between, but the way the needle is moving is exactly as in the new clock. So in particular, the fact that in the new clock, what the needle was doing is exactly reaching all the p hours, 0, 1, 2, all the way up to p minus 1. So all the hours, because p and q are co-prime. It means in the original clock, this needle is going through hours, multiples of g of this original one, right? So of this new one. So 0g all the way to g times p minus 1. Those are the positions that the needle is going through in the original clock. Okay, so that the answer for that then is P, right? The hours that are reached are the hours 0, g times 2 all the way to g times p minus 1. There are p hours, and p, remember, was m divided by g, because m was g times p. And so p is m divided by g, where g was the GCD of m and n. So that's the answer for how many hours are reached. And in fact, we know exactly which hours are reached, right? These are the multiples of the GCD, these many multiples of the GCD. Let me round it off with the last question here. What is the first hour that gets repeated, right? So here is, if you look at an hour, which is say 3 here, which is co-prime with m, actually it looks strange, right? Nothing is repeated. That's what I told you. Nothing would repeat. But actually, if you let the clock run for one more step, this is what you have. You will be back at 0 because m times n is a multiple of m, no matter what n is. So in all these cases, you will be back at 0, which is m times n, it's a multiple of m. So yeah, so this tells you that at least for m and n, when n is co-prime with m, 0 is the first digit that repeats, first number that repeats. And that's good enough then, since we know this correspondence between the any clock and the new clock we built by dividing by the GCD, we know that in that new clock, 0 is the first digit that repeats. So it must be the same in the original clock, because the original clock can be retrieved from this new clock by multiplying everything by G. So the first repeated position will still remain 0. Alternately, here is another, maybe a simpler argument to see 0 is the first thing that needs to be repeated. So take any two positions that repeated, right, in your n. So think of this as an infinitely long row if you want. So somewhere, some two things have to repeat. So pick any such pair of time steps where the same hour is repeated. But now you can go back one step in time, and you know that, so if you reached 4 by adding 2 to something, in the previous step also, the needles should have been in the same positions, right? So at time t minus 1, and so say this was t1 and t2, they were at same place. Then at t1 minus 1 and t2 minus 1 also, they should have been in the same position. And you can keep doing this. You can keep going back in time and maintain, keep a pair of time steps which have the same position until you hit, until this first one is equal to 0. And then you cannot go to the left. And you see that, then, well, so what does this tell you? That whenever you find some things other, so here you cannot go back any further, okay? So for any other, say, when you started with something like this, like 2 or 4, any other positions you start off with, if they were to be the first positions where a number repeated, well, they can't be, because there will be one, before them, and then, one before them, and so forth. The only case where this argument does not work is when one of them is the first position, and that is 0. So that's another way to see that the first digit that first number that repeats has to be 0. All right, so that's answer to that question also.